Here's another way to use the where method. Search and operators perform comparisons between two values. The result of a comparison expression is a bool value, and there are only two bool values, true and false. We've already seen assignment statements like these. Comparison expressions like these and like these are a bit different. So these 6 comparison expressions have a different role in Python than the 2 assignment statements at the top. Assignment changes a name to refer to a new value. Comparison expressions check whether some expression is true or false. So they might check whether x is greater than 1, or in this case, whether x and y are 2 equal values. So the double equals you see here is used to distinguish from the single equals that performs assignment. Double equals checks whether x and y are equal. It does not change either x or y. Here's how you write does not equal to. And it's even possible to chain comparisons, although this is much rarer in practice than just comparing 2 values at a time. Here's greater than or equals, that's greater than, that's less than. Okay, when you use t.where, you're welcome to give it 2 arguments, the label of a column and some comparison like r.equal_to. Or you can pass an array of bool values, an array of trues or falses, and what you'll get back is a table with only the rows of t for which the corresponding bool is true. Let's take a look at how we'll use this. I can check that 2 is less than 3. It is. I can check that 2 is less than 1. It is not. Those are the true and false values. Now, it's very rare that you'd have 2 different constants compared because you already know the answer. But you might do some big computation. And then check, is x greater than 5? And now you know that it is. If I compare an array to a constant, then I'll figure out which ones are greater and which ones aren't. For example, here's a range of 0, 1, 2, 3, 4. If I ask which of these are equal to 2, I'll find that only 2 is equal to 2. So I see a true there and false otherwise. If I ask which of these are less than 4, I'll find that 0, 1, 2, and 3 are all less than 4. I can even compare one array to another array as long as they have the same length. When is it the case that the value in a range 5, 0, 1, 2, 3, 4, is less than the corresponding value here? So 0 is less than 2, 1 is less than 2, 2 is not less than 2, 3 is less than 5, and 4 is not less than 1, which is why we get true, true, false, true, false. So I'm comparing this value to that value, and likewise each corresponding value using this comparison each time. So how does this all interact with where? Well, let's see using a real data set. Each row here tells me the population in 2010 and 2015 of some category of people residing in the US. Here we have sex, which indicates 0 for both, 1 for male, 2 for female, and then age is a year. So if I look at the US population table, where age is 70, I'll get 3 rows, and this is the sum of these two. If I don't want this row, and I only want those 2 rows, as you know, we could exclude 0. Or we could take 1 and 2. But a third option is that we could where and say, I don't want 0, I do want 1, I do want 2. And I'll get the same result. Now, you would never write out false, true, true. Instead, you typically compute which ones you want. Let's say this is all the rows corresponding to H70, I might look at where 70 dot column 2015 is less than 2 million. And then I'd get that false true true. So if I said 70 dot where this expression, I'd get the rows for which column 2015 is less than 2 million. I call this an advanced version of where because it can allow us to perform where queries that we couldn't perform just by talking about one column at a time. So for example, I could take the whole table. I could figure out when it's the case that the ratio between the value in the 2015 column and the value in the 2010 column is really large. How about greater than 1.5? That's almost never true, but occasionally it is. If I want to figure out when it's true, then I would put this expression inside of a where. USPOP.where. I don't have to say which column I'm checking. Instead, this just tells me which rows to keep. I keep the rows where the corresponding value is true, and I see that it's only among males from 94 to 100 that we see this huge ratio of more than 50% more people in that age range in 2015 than 2010. Hooray for modern medicine. There's the trip table again. I wonder what the average duration of a bicycle trip is. np.average trip.column duration. 550 seconds. Does it take longer or shorter if you start and end at the same place? You could imagine either way. The start and the end are really close to each other, so you might imagine it's a short trip. Or it requires some round trip where you start somewhere, you go somewhere, and then you come back in order to start and end at the same location. That sounds like it should take longer than just starting in one place and ending in another. Well, let's figure out which it is. I can say trip.column start equals, and I have to use two equals to say I'm comparing, trip.column end. This will tell me which rows, which trips, have the same start and end location. Then, I take an average of all the rows in this table where that condition is true, grab their durations, and now I'll know that the average trip that starts and ends at the same place is 759 seconds, which is longer than the average for places that start and end in different. So the one-ways are shorter than the round trips. Now you'll notice this average is almost the same as this, whereas this average is much greater. How is that possible? Well, there are just many more trips where the start and end are different. And we can see how many by asking for the number of rows, 333,000 out of 338 is that over 98% of the trips are one way. But this small fraction of round trip trips are on average longer. And we couldn't have figured this out without this advanced version of where that lets us consider two columns at once.